probability, and we want to consider some examples. We are given two events A and B, and the probability of A is 0.3, probability of B is 0.5, and probability of negation of A intersection B is 0.35. So we want to determine whether events A and B are independent or not. Then what we know is that probability of A intersection B would be probability of A times probability of B. So that's something that we want to keep in mind, that when they are independent, that's how we get their respective probabilities. We know that probability of A not A should be 1 minus probability of A, which is 1 minus 0.3, which is 0.7. Therefore, what you're basically saying is that probability of A intersection B independent if this is true. And from what we have been given, we are told this is 0.35 and this is 0.7 times 0.5 and this is 0.35. So because that is true, then it's very easy to tell that the two events are independent of each other. So we can comfortably say that event A and B are independent. So that's something we want to keep in mind as we calculate the probabilities. We are told to find probability of A union B, and since we don't know much about the issue of independence here, we can write probability of A union B as probability of A plus probability of B minus probability of A intersection B. And since we know that A and B are independent, it will be 0.7 plus 0.5 minus 0.7 times 0.5. And this is 1.2 minus 0.35, and this gives us 0.85. So that is the probability of A union B. Second example. Our second example, a single fair dice is loaded. So we have a number of questions. We list the sample space for a single dice, and the S is all the numbers that are equally likely to occur. And so in our second example, the first part you have shown the sample space, the second part you are told to let event A be equals to all the even outcome and event B to be the outcome divisible by 3. So probability of A will be all the numbers. You have 2, 4, 6, which is 3 over 6, which is a half. And then probability of B are all the numbers divisible by 3, which is 3 and 6, which is 2 over 6, which is 1 over 3. One of them is we want to find probability of A intersection B. Remember that A is equals to 2, 4, 6 and B is equals to 3 and 6. So that is what we have, and therefore I can comfortably say that A intersection B should be equals to 6. So probability of A intersection B is only one element out of the total number of elements that exist, and which is equals to 1 over 6. They are only independent if probability of A intersection B is equals probability of A times probability of B. And since it's 1 over 6, we saw this is a half times that, which is also 1 over 6. Thus, A and B are independent. So number 3, a problem is given to 3 people, A, B, and C, whose respective chances of solving it are 1 over 5, 1 over 3, and 2 over 5 respectively. What is the probability that the problem is solved? So the probability of the problem being solved will be equals to 1 minus the probability that it is not solved. And since the probability of solving for each of the person is independent of the other, then we can write this as 1 minus the probability of A not solving it is 4 over 5, because the probability of solving is 1 over 5. The probability of B not solving it is 2 over 3, and the probability of C not solving it is 3 over 5. And therefore when we cancel, it will be 1 minus 8 over 25, which is equals to 17 over 25. So there is a 17 over 25 chance, or if you wish, we can write it, there is a 68% chance that they will solve the problem. For number 4, we are told that out of 200 students in a school, 60 play cricket only, 80 play football only, 55 will play volleyball only, and 5 play no games. And when you look at 60 plus 80 plus 55 plus 5, that should be equals to 200 students. So one student is picked at random. What is the probability that he plays volleyball? Therefore, probability of volleyball should be the number that play volleyball, and we can see that they are 55 divided by 200, which is 11 over 40. So that is the probability that a student plays volleyball in the school. He or she either plays cricket or volleyball. So it's take the number of those who play cricket and the number that plays volleyball, divided by the total number of students, which is 115 over 200. And if we divide by 5, this will be 23 over 40. So there's 23 over 40 chance that a student will play cricket or volleyball. So plays cricket nor football, it will be 200 minus 60 minus 80 over 200, which is 60 over 200, and that is by 23 by 2010. There is a 3 over 10 chance that he plays neither of the indicated games. If at least one child in a family with 2 children is a boy, what is the probability that both children are boys? So what the question is telling us is that this family has 2 children. So we want to put down the sample space. They could both be boys. They could be both be girls. We could have the firstborn as boy and the second one as a girl, or the firstborn as a boy and the second one as a girl. And so we have 3 outcomes. So the probability that both are boys is the probability of a boy over the total possible outcome. Therefore, the probability that both of them are boys is 1 over 3. We consider the binomial distribution with an example. 60% of people pass the driving test on the first try. So whenever there is a test, 60% will pass the test the first time. A group of 30 individuals who have taken the driver's exam is randomly selected. Calculate the probability that first part 5 pass the exam. And for us to be able to do that, we start by giving the probability mass function. It's called a probability mass function for the binomial distribution, PMF. which is given by probability of x is equals to x is equals n combination x px q raised to power n minus x. So in this example that we have, the first thing is that we are told n is 30 and the probability is 60%, so the q is equals to 0.4. Why do we say that? Because we know that p plus q is equals to 1. So if we are told 5 pass the exam, we are interested in getting probability that x is equals to 5. So whenever there is n, I put 30 and x I put 5. And this is 0.6 to power 5, 0.4 to power 30 minus 5. And that's what we have. And that's the computations that you are supposed to do. So this, without doing all the maths, is 30 plus factorial over 25 factorial, 5 factorial, 0.6 to power 5, 0.4 to power 25. Probability is very low, 1.2476 times 10 raised to power negative 6. So probability that x is equals to 30 is 30 factorial, 30 factorial, 0 factorial, 0.6 to power 30 and 0.4 to power 0. It's 2.211 times 10 raised to power negative 7. That's the probability that all the 30 will pass the exam. So at most 2 pass the exam is probability x is equals less than or equals to 2. The probability of at most 2 pass the exam is probability of x less than or equals to 2. So its probability of x is equals to 0 plus probability of x is equals to 1 plus probability of x is equals to 2. And this can be written as 30 factorial, 0 factorial, 30 factorial, 0.6 to power 0, 0.4 to power 30, plus 30 factorial, 1 factorial, 29 factorial, 0.6 to power 1, 0.4 to power 29, and then the third one will be equals to plus 30 factorial, 2 factorial, 28 factorial, 0.6 to power 2, 0.4 to power 28. So when we compute all that and we put them together, that gives us the probability. Probability that at most 2 will pass the exam will be given by 1.183 times 10 raised to power negative 9. So it will be probability of x greater than or equals to 3, which will be probability of x is equals to 3 plus probability of x is equals to 4, all the way until probability of x is equals to 30. And this is the same as 1 minus probability of x is equals to 0 plus probability of x is equals to 1 plus probability of x is equals to 2. And so that's what we have as probabilities, and this is the same as 1 minus 1.183 times 10 raised to power negative 9, and this is a probability of 0.999, which is approximately equals to 1. There is a 100% chance that at least 3 people, because we are told 60%, and already 60% of that is 18. So that's why the probability is very high that at least 3 will pass the exam. Second example, we are told that x is approximately binomial. This is our p and this is our n. Therefore, automatically our q is 0.3. Then we are told to find probability of x is equals to 2, which is 6 factorial, 2 factorial, 4 factorial, 0.7 to power 2, 0.3 to power 4. And that gives me 0.0595. Expected of x, which is n times p, which is 6 times 0.7, which is given by 4.2. And c, the variance of x is npq, which is 6 times 0.7 times 0.3, and that gives me 1.26. So given the value of x, and then you are given the p of x, or sometimes we use the f of x. And so since n is 4, n is equals to 4, so x will start from 0, 1, 2, 3, and 4. So we have 0, 1, 2, 3, and 4. And I'll give you the probabilities and I'll show you how to calculate them. So one thing in common is this plus this plus this plus this plus this should be equals to 1. So if you sum all the probabilities, it should always be equals to 1. Now how do we get them? The only value that is changing is x. The p remains and the q remains. So the first one is probability of x is equals to 0, which is 4 factorial, 0 factorial, 4 factorial, 0.6 raised to power 0, and 0.4 raised to power 4. And if you do that, 0.4 raised to power 4 should give you 0.0256. 0.0256. The second one is probability of x is equals to 1, and that should give us 0.1536. How do we get that? It's 4 factorial, 1 factorial, 3 factorial, 0.6 to power 1, 0.4 to power 3. And then the next one will be probability of x is equals to 2, and this should give us 0.3456, which is 4 factorial, 2 factorial, 2 factorial, 0.6 squared, and 0.4 squared. And that should give us that value. And then the next value, which is x is equals to 3, probability of x is equals to 3, which is 0.3456, is 4 factorial, 3 factorial, 1 factorial, 0.6 to power 3, 0.4 to power 1. And then finally, probability of x is equals to 4, which is 0.1296, is 4 factorial, 4 factorial, 0 factorial, 0.6 to power 4, 0.4 to power 0. So that is how you would go about calculating the probabilities for binomial distribution. Poisson distribution, and we have the probability mass function for Poisson distribution. The px is equals to e raised to power negative lambda, lambda to power x over x factorial, and x starts from 0, 1, 2, and so forth. We consider an example. An answering machine receives about 8 telephone calls between 8 a.m. and 10 a.m. What is the probability that the answering machine receives exactly 2 calls in the time interval? So the first thing is we want to get the mean, which is the number of calls, and we know here the time is 2 hours. That's what we want to keep in mind. We'll use, but we'll keep the time period. So we are looking for the probability that x is equals to 2. And since we have said the formula is given by e raised to power negative 8, which is our lambda, and then lambda to x, which is 8 squared, and then the last thing is over 2 factorial. So that's what we have, and therefore that will be 8 squared is 64 over 2 e raised to power negative 8, which is that 2 e raised to power 8. So that is the probability that you will receive exactly 2 calls. Part B of the question, that the answering machine receives at most 2 calls in the time interval. probability of at most x is less than or equals to 2, so it's probability that x is equals to 0 plus probability of x is equals to 1 plus probability of x is equals to 2, which we've already been able to work on previously. So if that's the case, it is e raised to power 8 to the power 0 over 0 factorial plus e raised to power 8 to the power 1 all over 1 factorial plus e raised to the power negative 8 squared all over 2 factorial. So this is e minus 8 plus 8e minus 8 plus that 2e minus 8, which is 41 e raised to power minus 8, and is also equals to 0.0138. So there is a 1.38% chance that it will receive less than 2 equals to 2 or less than 2 phone calls in that time period. But see that the answering machine receives at least 3 calls in the time interval, so its probability that x is greater than or equals to 3. So we look at all the possible probabilities up to infinity. So and this is the same as 1 minus probability of x less than or equals to 2. That's basically what we have. So it is 1 minus 0.0138, and that will give us 0.9862. So there is a very high chance that at least it will receive a minimum of 3 calls or more. And that is okay because on average it receives 8 calls in that time interval. So that the fourth one is that the answering machine receives more than 1 call in the next 15 minutes. So what happens is that we say that lambda is equals 8 for 120 minutes. So now we have to get a new lambda, which is 15 over 120 times 8 is equals 1. This is for 15 minutes. So now our lambda value changes because we have changed the time interval. So therefore we want to find that it receives more than 1 call, so it is greater than 1. So is equals to probability of x is equals to 2 plus probability of x is equals to 3 all the way, which is 1 minus probability of x is equals to 0 plus probability of x is equals to 1. So that's for probability of x is equals to 0, it is e raised to power negative lambda, and we know what is our new lambda, and then our lambda is 1 raised to power 0 over 0 factorial, which is e raised to power negative 1. Then the second case is probability of x is equals to 1. That's what we are calculating. So it will be e raised to power negative 1, 1 to power 1 all over 1 factorial, which is e raised to power negative 1. We can say therefore that probability of x is greater than 1 is equals to 1 minus e raised to power negative 1. These two, when you sum them together, that is the value they give, and this is 1 minus 0.7358, which is equals to 0.2642. So now when the time period changes, for example, you want to change now from the 2 hours, that is 120 minutes, we are told that lambda is equals to 8. Then somebody says 60 minutes. So our new lambda will be 60 over 120 times 8, and that will give us 4. So whatever now you'll be working with, you have reduced the time period from 120 minutes to 60 minutes. Then your lambda value changes, but everything else remains the same when we are solving such problems in future. Number 2, given that x is approximately Poisson with parameter 2, and our parameter 2 here is lambda. Basically, we are saying that our lambda is 2. Find the probability that x is equals to 1. It is e raised to power minus lambda, lambda raised to power 1 all over 1 factorial, which is 2 e raised to power minus 2, which is 0.2702. We could also be asked to find probability of x is greater than 1, which is from probability of x is equals to 2 plus probability of x is equals to 3 going forward in that increment. This is the same as 1 minus probability of x is equals to 0 plus probability of x is equals to 1. And we've got the probability of x is equals to 1 as 0.2707. So probability of x is equals to 0 is e raised to power minus lambda, lambda raised to power x over x factorial, which is e raised to power minus 2. So probability of x is equals to 0 plus probability of x is equals to 1 will give me 3 e raised to power minus 2. And therefore, probability of x greater than 1 is 1 minus 3 e raised to power minus 2. And if you do some computation, you get 0.594. And that's a solution to that question if we have been given the parameter lambda for a Poisson distribution. Exponential distribution. The probability density function of an exponential distribution px is equals to 1 over mu e raised to power negative x over mu, where x is greater than 0. We have an example, the life in years of a certain type of electrical switch as an exponential distribution with an average life of mu is equals to 2. It could be 2 years or 2 months, depending with the information. What is the probability that it fails during the first year? And therefore, that means probability of x is less than or equals to 1. So it is from 0 to 1, 1 over mu e raised to power negative x over mu dx. And we know that mu is equals to 2. So if we do the computation, it will give us negative e raised to power negative x over mu. And we know what is the value of mu. Mu is 2, 0 to 1. So after that integral, I can substitute the value of mu. So I have negative e raised to a negative x over mu, 0 to 1, which is negative e, and we have said we need to substitute the value of mu so that we are working with numbers. It will negative 1 over 2 minus e raised to power 0. So and this is 1 minus e raised to power minus 1 over 2. So that is the probability that it will fail within the first 1 year. So since mu is in years, it fails within the 2 to 4 years. So I'll be looking for the probability that x will lie in that interval. So it is 2 to 4, 1 over 2 e raised to x over 2 dx. And this is equals to minus e raised to minus x over 2, 2 and 4. It tells us that it's minus e raised to power minus 4 over 2 plus e raised to power minus 2 over 2. So it is e raised to power 1 minus e raised to power minus 2. And that gives us the probability that it will fail between 2 and 4 years. For number 2, the number of days ahead travelers purchase their airline tickets can be modeled by an exponential distribution with an average amount time equal to 15 days. Find the probability that a traveler will purchase a ticket fewer than 10 days in advance. So what we have been given here is our mu, and we have been told it's 15 days, and we are told fewer than 10 days. So we want to find that probability, and we want to integrate from 0 to 10, 1 over 15 e raised to power x over 15 dx. and that will give us negative e raised to power x over 15 between 0 and 10 days. So that's what we want to work with for that example. And this gives me e raised to power negative 10 over 15, which is 2 over 3 plus e raised to power 0. So it is 1 minus e raised to power negative 2 over 3, and that will give us 0.486. Part B, how many days do half of the travelers wait? And definitely we have been told that the integral from 0 to 10 of 1 over 15 e raised to power negative x over 15 dx is equals to 0.486, which is approximately 48.6%, or if you wish, you can say it is 49%. And this is half of the time. So the travelers wait for an average of 10 days. But there are other ways of going about it if we are not sure on how to, if that was the actual value. We could have said that we want to find the probability that x is less than t, which is the integral of 0 to t 1 over 15 e raised to power minus x over 15 dx. And that will give me minus e raised to power minus x over 15, 0 to t. And this will give me 1 minus e raised to power minus t over 15. And this should be equals to 0.5, which is half of the time. If I rewrite my equation, then it means that e minus t over 15 is equals to 1 minus 0.5, which is 0.5. And that's what we have. Then I introduce the natural logarithm on both sides. So I introduce ln of e minus t over 15 is equals to L of 0.5, which is equals to negative 0.693. And therefore, negative t over 15 is equals to negative 0.693. Definitely the negative signs will cancel, and we'll be able to get the average value of t. And t is equals to 10.39 days. And we could say it's approximately 10 days, like what we got in the previous example. Part C, what is the probability that a traveler will purchase a ticket after 15 days? And so want to find probability of x greater than 15, which will be equals to 15 to infinity 1 over 15 e raised to a minus x over 15 dx. And this will be equals to negative e raised to a negative x over 15, 15 and infinity. So it is e raised to power infinity plus e raised to power negative 1. And the answer will be e raised to power negative 1. Alternatively, we could have said probability of x greater than 15 is 1 minus probability of x less than or equals to 15. So first of all, I would get probability of x less than or equals to 15, which is the integral from 0 to 15, 1 over 15 e raised to negative x over 15 dx. And that will give me negative e raised to negative x over 15, 0 and 15. So if I do that, it will give me 1 minus e raised to power negative 1. And therefore, probability of x greater than 15 is equals to 1 minus e raised to power minus 1, which is e raised to power negative 1, just like in the previous example. And this is equals to 0.367. So whichever way you'd follow, you'll come to the same solution. want to see how we can read the standard normal distribution tables. And this is the table that I want to use. There are so many others out there, but today I want to spend a bit of time looking at how to read through this. So when you look at it, you see that on there is a z here, and there are values below it, and the values going sideways, and then in between here we have more values. So we'll be looking at the z values, and when you look at the diagram on top here, it tells you from 0 to z. So what we normally have is this. These are the z axis, both the negative and the positive, and then the center is at 0. So now we are told, for example, to read this area. Maybe if I give you a value like 1.1, so somebody tells you read for us this. How do we go about it? From the positive side, we look for 1.1, and the 1.1 is here. So the area under the curve is 0.3643. This one is 0.3643. Now, if it was 1.14, then things would have been different. We are not far off. You come to 1.1, which is here, and then you look for this 4. So where these two meet is this value. It is 0.3729, and that will read for us the value on the positive. The other thing I've not mentioned is that for a normal distribution curve, because of symmetry, we take this side to be 0.5, and this is 0.5. So technically, it tells me that if I know this part, then this other part that I'm shading with a different color, I can be able to get it, the red part, which will be basically be 0.5 minus 0.3729. And that will give me this part, because one end, all of it is 0.5. And if I know a portion of it, I'll be able to get the equivalent part on it. And the same case would apply if I'm dealing with the negative side. So for example, I have a curve, and on this end, I'm told this is negative 1.14. And I'm told to find this area. Because of symmetry of this, then this portion is equals to this. So this portion will be equals to 0.3729. So they will be equivalent because of symmetry. They are symmetrical. The normal distribution curve is symmetrical. Now, based on that, which you can download from the internet easily, I want to go through a couple of examples to see if we are comfortable going through the tables on our own. So I want to draw quite a number of them, and then we'll be looking at them one by one. And we have an example here. So if I gave you this, and then I gave you a value like 1.0, and then I'll give you the equivalent of negative 1.0. So what we have said is, if this is AB, then this is also on this side, this will be AB. So B are equal and A are equal. That is one thing we want to keep in mind, because this is a z-axis on the positive, and this is a z-axis on the negative. So if I have a value like 1.8 on the positive, or if somebody tells me, oh, I want you to get the 1.8, that will be easy. I'll go to the tables as we have been doing and look for 1.8, and it will tell me this is 0.4641. But then I could as well have said, okay, I don't want the value 1.8 on the left, I want it on this side. What will be this value? this value will be 0.0359. How did I get 0.03? I'll take 0.5 minus 0.4641. Remember, 4641 is here, and so that all that side will be 0.5. Now if somebody gave me this and said, okay, now I have a value on the negative, so I give you negative 1.8 and I tell you to get this. So you go to the tables, because the tables are only on the positive side. Remember, it is the z value that is negative, not the area or the probability. So this will be equals to 0.4641. So you have only values on the positive. If we go back to our diagram above, and then we use those positive values, like here it's 1.80, so it is 0.4641, and that's the exact value that we are using to be able to compute that. Then finally, maybe you could be given a question like, the shaded part is what I am requiring, or that what I'm interested in. So if I put 0 here, and maybe I put negative 1.75, so if I want the shaded part, the first thing is I have to know what is the area of this part here. This is 0.4599, and so once I subtract from 0.5, I'll get the shaded part, and therefore that will give me 0.0401. So that is the procedure of going about getting the probabilities from the standard normal. Sometimes you're given a bigger margin, and I'll show you another example. Maybe somebody says, can you get us the area of the shaded part? Negative 0.8. Then somebody shades all this. What we know is on the positive, this is 0.5. So we go to the tables and look for this portion, and this is 0.2881. So the total area will be 0.2881 plus 0.5, which is 0.7881, and that will give us the whole area or the probability that you're interested in. Finally, the same could apply, whereby this time it is maybe the value on the positive. Maybe I give you a value like 1.25, and I'm giving you all this portion. Again, this is 0.5, and then I go to the tables and get 1.25, and that will give me 0.3944, and therefore the total area will be 0.5 plus 0.3944, which is 0.8944, and therefore that gives me the area of that curve. Finally, I can give you other examples. For example, you are told to calculate the probabilities. The first one is you are told that probability of z is less than 0.3. The best thing you can do for yourself is you try to sketch the curve. Then you put 0.3. You ask yourself, which part are we interested in? You're interested in all this portion. And that, if you go to your tables, you'll get is 6179. So you get 0.03 here, which is 0.1179, and then you add to 0.5. If you sum the two, you'll end up getting that probability. And the final one that we would want to consider, which I didn't do, is if I want to get 0.5 and 0.9. So again, you sketch your graph and see where the values will fall. And then this is 0.5 and this is 0.9. So I'm interested in the area between these two. So what you do is when you get 0.9, it will give you all this portion, then you subtract. So the 0.9 is 0.3159 minus 0.15 is 0.1915, and the difference between the two gives us the probability that we are interested in of the area under that curve. So this is the process that you take when you're calculating or reading the standard normal distribution tables. Normal distribution, we are told that the distribution of men's height in a classroom measured in centimeter is normally distributed with a mean of 175 centimeters and the standard deviation of 6 squared. So the standard deviation here is 6 and the variance is 6 squared. Find the probability that a man is less than 169 centimeter tall. And so we want to apply the principles of the normal distribution. We have been given our mu as 175, our sigma as 6. So we want to find the probability that the person is less than 169 centimeters tall, and therefore the idea we want to use is we want to transform the normal distribution to the standard normal using this formula. This is what we call the standard normal distribution. And why do we want to write it in standard normal? So that we can use the statistical tables to get the value. Statistical tables to get the value. So that's why the transformation will be necessary to put it in an interval of the standard normal distribution. So therefore we have probability of z less than 169 minus mu 175 all over 6, and this is probability that z is less than negative 1. So the next step is to put this into the standard normal diagram. And we want this area. And according to the table, what's the area? The area is 0.1587, the shaded part. And that is the probability that a man will be 169 centimeters or less. Now the probability that x is greater than 190, which is the probability z is greater than 190 minus 175 divided by 6. Remember we said that z is equals to x minus mu divided by sigma. So when we put down this, it helps us to be able to compute the values. Probability that z is greater than 2.5. Again, we come to the diagram, just a sketch to give us an idea of what we need. I put 2.5 and I want greater than. And if I go to my statistical tables, this will give me 0.0062. So there is a very low probability that you'll find a man who is more than 190 centimeters. Saying that the centimeter is 175 with a standard deviation of 6 centimeters. So that is what the question is saying. So we'd expect the most people to be between 169 and 181 centimeters. That is where majority will lie. We want to find a probability that a person lies between 169. It will be probability 169 minus 175 divided by 6 less than z less than 190 minus 175 over 6. So it will be because probability -1 is less than z is less than 2.5. And so you come again to the diagram. This is always the guiding point. You put your values and you want now to find which part are you interested in. And if you get the part, then you will be able to easily find the probability. So there is a 83.5 chance that a man will have an height of between 1.169 centimeters and 190 centimeters. For number 2, we are told that if z is normally distributed with a mean of 0 and a standard deviation of 1, we find a number of probabilities. And this is what we call a standard normal distribution. If I had said x is 0 mu over sigma, this is the normal distribution. And for you to move from normal distribution to standard normal, which is z of 0, 1, and this is x of mu sigma, what you do is you standardize using the formula. So that is where you have to standardize your normal distribution, and so we say you standardize with z is equals to x minus mu over sigma. So if you move, you come here, you'll end up there. So that is what we have been doing. But now what you have been given, the first example, it was a normal distribution. In the second example, it is a standard normal. That's why in the first example, you use x and then we transformed to z. But this time, we have been given the z. So if you are told to find probability z is less than 1.2, what you do is you go to draw a curve, then you get your normal distribution table, 1.2, and therefore this is less than. So less than 1.2, it means it is this part plus this part. And so you need to find out what is your 1.2 is 0.3849, and we know that this part is 0.5. So this I can comfortably say is 0.8849 as the answer to that using your standard normal table. Can think of another example. We find probability of z less than negative 0.5. Again, we come here, we make a sketch of what we need. I can put negative 0.5 there. I need to find this. So the thing I go to find is this. I look for 0.05, which is 0.1915, and therefore this will be 0.5 minus 0.1915, and that's the procedure, and this will give me 0.3085. We could also get one more. Probability of z greater than 0.8. So what we do is we come here and then we put 0 and then we put 0.8. We want greater than. Now if you go to your tables, the one I'm using, and look for the value of 0.8, it will give you that, which is 0.2881. So for me to be able to get the shaded part, it will be equals to 0.5 minus 0.2881, and that will give me the value of the part that I'm interested in. So our third example, given z to be a standard normal, find the z value for which the area to the left of z is 0.2119. So the first thing we want to do is we want to make a sketch, and what we know is that area is on the left, is this side. So it should be, the area I'm interested in should be this. It should be 0.2119. Now if I go to the tables, I should be able to get this, and this should be 0.2881. Now when I go to my statistical table and look for 0.2881, it tells me that this point should be. So 0. So the value of z should be equals to negative 0.81. So the question is probability that z is less than negative 0.81 should be equals to 0.2119. That's what the question is asking me in other terms. Invoices at a particular depot have amounts which follow a normal distribution with a mu, that is a mean of 900 and a standard deviation of 50. What percentage of invoices will have an amount above 1000? What is the probability that x will be greater than 1000? So we want to transform this to a standard normal. 1000 minus 900 all over 50. And we are looking at the probability that z is. And so what we do as usual is we put in the table the normal distribution curve, and we shade the part that we require. And if we do that math, it will be 0.0179. Now, because I know this part will be equals to 0.4821, and so for me to get this part, it will be 0.5 minus 0.4821. And if you do that, you'll find that that will give you the answer to that section. Part B, about what amount will 80.23% of invoices lie? And this is what we are interested in, which is 900. Where will 80% of the invoices lie? So we want to find out where will this be. So we want to find out this amount. That's the question. 80%. Where will they lie? The few others will lie on either, but where will they be? So that's the question we want to be able to answer. So we want to find probability that x greater than a certain amount a should be equals to 0.8023. So if I transform this, it will be probability of z is greater than a minus 900 all over 50 is equals to 0.8023. Now, we go to the statistical table and read in the value of z, 0.83. So what we have is, we already know that this is 0.5. This is known. What we don't know is this part, 0.3023. And what will be the value there? So if we look for 0.023, it will be 0.85. It will be negative 0.85. So I can comfortably say probability z greater than negative 0.85 is equals to 0.8023. Now, there is a relationship between this part, this component, and this component here. That's what we are saying. Therefore, I can equate them. I can say a minus 900 all over 50 is equals to negative 0.85. Therefore, a is equals to 50 times 0.85 plus 900. This will be equals to, remember there is a negative, negative 42.5 plus 900. 857.5. So any amount 857. So what we are saying is this, that 80.23% of invoices will have an amount of 857.5 and above. And that is true. we can show that to be the case. Let's go through it again. So what we are saying is probability of x greater than 857.5 is probability of z greater than 857.5 minus 900 all over 50, and equals to probability z is greater than negative 42.5 over 50, which is probability of z is greater than negative 0.85. And because it's greater than, we'll be looking at this part. And that shaded part will give us 0.8023. And so that's the question that we were trying to answer with that information. Above what amount will 80.23% of the invoices lie? Thank you for watching.